write expression and example, explain nuclear resonance. This was again a question which I asked. Okay, so as I keep on giving you each and every topic, every time I am telling you what are the possible questions. But then this is a descriptive question. Okay, so this is a descriptive question, and that is important. So whenever we are actually talking about a nuclear reaction, what happens is we are more or less considering heavier nuclei or a lighter nuclei, right? Because, for example, one of the most popular example is like bombarding uranium-238 with neutron. Okay? So if you're basically considering a nuclear reactor, you do understand that you bombard uranium with a neutron, and then that will actually give rise to an unstable nuclei, okay, an unstable uranium. And it will also give rise to some more neutrons which comes out, but we are not considering that reaction. Okay, so what happens is we do have a neutron here, and then this is your gamma, so there is some energy which is actually going out. Okay, and then if we consider this, what happens is that we don't have any outgoing particle right now, we have just some energy which is coming out. Okay, and the unstable nuclei is uranium here, and the stable nuclei is uranium-238. Okay, so this is a nuclear reaction, how you represent it. And let's go step by step now. The first thing is we can write down what is the Q value, right? So if you are having any kind of nuclear reaction, okay, we do have something which we call as the Q value. So what is basically a Q value? Q value is nothing but you can consider what is the energy that is produced in this two minus the energy that is here. Okay, and if that value is positive, we basically call it as a favorable reaction. So that means that reaction energetically it's possible, right? So when you talk about the Q value here, it is mnc square plus m into 238 uranium c square, okay, mass of this, minus mass of uranium-239 into c square. So when we actually studied about binding energy, we did see how to know the mass, okay, and how to get it in AMU, how to convert it into MeV and so on. Okay, so if you do this calculation, you can do it on your own and you can get an answer which is something similar. Okay, so the answer is 4.86 MeV. Okay, so this is the energy difference that we are getting here, and this is the Q value. So for understanding resonance, we start from the Q value part. Okay, so in general, what happens is if this is your target, and if you're bombarding it with a neutron, okay, a neutron, then what happens is the neutron will actually have some kind of kinetic energy, and this will actually be at rest. So just as I said yesterday, that if it is at rest, the velocity here is 0. So that means this kinetic energy will be 0 for this, okay, before the reaction happens or before the scattering happens. Okay. On the other hand, in this particular case, a neutron is moving, so it will both have rest mass energy as well as kinetic energy. But this will have only rest mass energy, no kinetic energy. And then after the reaction, this is the sample that we have. We're not really looking into the fact that uranium-239 will break up into barium and krypton or any other component, okay? But right now we're just concentrating on the excited state, okay? And then we'll understand what is nuclear resonance. So we know that if it is basically a reaction which should be favorable, the linear momentum is conserved and also the energy is conserved. So what do I mean by linear momentum is conserved? Initially, when we had only neutron, this will have a momentum, right? But the uranium-238 part won't have any momentum. So this will have a momentum. This must be equal to the momentum that has been transferred, okay? And then finally the momentum of uranium-239, okay? So uranium-239 or the single neutron, both will have the same momentum. So this is from momentum conservation, we have one relation. And then just like yesterday, we are also going to write down the expression for kinetic energy. So let's look into the kinetic energy expression now. So the kinetic energy of neutron will be there because it's in motion, right? It's hitting the target. And then it will definitely have a rest mass energy, Mn into c square, right? Then plus we have got the rest mass energy of the uranium-238. So you have these factors. On the other side, you have the rest mass energy of uranium-239 plus the kinetic energy of 239. We have to remember that the energy of neutron is transferred to uranium-239, so it will definitely have some kinetic energy. Okay, we're not really looking into the magnitude. And then if there is a Q value, that means there is some energy lost in the process, okay, and that energy is nothing but delta E. So this also should be taken into consideration, okay. So if you are considering this uranium-238 jumping into uranium-239, it is basically getting excited, right, and getting jumping to your higher energy level. So if you are considering this, that means that we can say that this is the excited state, right? So the energy delta E will be actually because the uranium-238 has jumped to the excited state and it is uranium-239 now, okay? So we again, just like same as yesterday, kinetic energy of this resultant, that means uranium-239, we cannot control it, okay? We don't have any control on it, okay? We can definitely control what will be the energy of the incoming neutron, because we are bombarding it. We can use particle accelerators and we can apply a measured magnetic or electric field, and based on this we can say what will be the kinetic energy of the incident neutron. But after the reaction has happened, we really don't know what will be the kinetic energy of uranium-239, okay? So we actually need to eliminate this particular term, okay, so that we can get more meaningful information, okay? So what we do is this. So let's just write down this kinetic energy equation. It will be nothing but kinetic energy this plus Q. So if you remember, just now I said what is Q. So what is Q? Q is the difference in the rest mass energy on both sides, right? So this is your rest mass energy on this side, this is your rest mass energy on this side, okay? If you subtract one from the other, you basically get your Q value, right? And then you have to consider the kinetic energy also, right? So if you look into this particular equation, and if you just see this, you see this, you have these two terms minus this term. So what are the terms that we are eliminating here? This term plus this term minus of this term. So if you take these terms together, we get the Q value. So this is your Q, right? This is equal to the kinetic energy of uranium-239. So that is this part we have it now, plus delta E, plus delta E. So all the expressions are taken care of, okay? And see, it becomes a bit simple because we know what is the Q value in this particular reaction, okay? So then what we can do is we can write down everything in terms of momentum, okay? So uranium kinetic energy, you know, is nothing but P square by 2m. So P square of course, uranium-239 divided by 2 times of mass of uranium-239, right? Plus delta E. So we're just simplifying things here. We're not, we are not really finding out the result right now. Okay, we're going to look into nuclear resonance. So please, whenever you are to understand these things, remember your aim. Okay, and then only I think we'd be having a good approach to understand the problem. So let's see what happens now. So we are going to just do a slight change here. Okay, what we can do is we can write down this as Pn square divided by 2mn. Okay, we'll say why it is Pn square, because by conservation of momentum, momentum of neutron must be equal to the momentum of uranium-239. That was the first line, right? So we're just replacing uranium-239 momentum square by momentum square of neutron. Okay, but then divided by 2mn I have written. I cannot say that the mass of neutron is equal to the mass of uranium-239, obviously. So we have to just divide and multiply by mn. So dividing and multiplying so that we are not doing anything invalid here. And then we have got mass of uranium-239 plus delta E. Okay. So now you see what I have done is I have eliminated the kinetic energy part of uranium-239, about which I don't have any idea, okay, right now. I know about the kinetic energy of neutrons. So whatever I'm expressing it in terms of known terms, okay, not in terms of unknown terms. So what we have is, this is nothing but the kinetic energy of neutron. This is the kinetic energy of neutron, the kinetic energy of neutron into mass of neutron divided by mass of uranium-239, okay. So we have this, all these contents are known, and even this delta E can also be calculated, okay. So let's check now. So if we just take Kn on common, we have got it as 1 minus Mn divided by M uranium-239, right? Which is equal to delta E minus Q. Okay. So if you just look into this reaction, and let's say that the neutron has got a very less energy. Okay. So if the neutron is less energetic, the kinetic energy of the neutron can be considered to be almost zero. It won't be zero, of course, because it has to come and hit the target. But then if it is very less in energy, which usually happens when we are talking about compound reaction, okay, then what happens is that this part will actually become zero. If this part becomes zero, that means delta E is equal to Q. So if you recall, we also calculated binding energy. Okay, so when we calculated binding energy, we actually took a similar equation like the Q energy or the Q value equation that we have taken. So these are actually applicable for the bombardment which happens because of the lower energy projectiles. Okay, so neutron is having a lower energy, and that's why we can consider at that particular instant that delta E and Q are almost equal. Okay, so see, for all practical purposes, for all calculation purposes, if you consider delta E and Q as same, okay, it's not wrong. Okay, it's not wrong, but depends on the energy of the incident particle. So that's very important. So what we have found out, the Q value is 4.86 MeV. So whenever we are doing any kind of nuclear calculation, we started within our lower classes. We all started with something which we call as the binding energy, right? And then we also saw about Q value. So if you consider any kind of reaction, we are talking about the Q value, okay? And we are also talking about binding energy, but most of the times we see that the binding energy and the Q value more or less gives you similar values, results, okay? But then if you're considering this nuclear resonance problem, and if you understand this, you see that Q value and the energy or the binding energy, the E value that we use there is more or less the same, okay? So why we call it as nuclear resonance is our next topic, okay? So what we can say is that the excitation by capturing the neutron. So this is nothing but the excitation happening by capturing the neutron. So what happens is, if you are having a uranium-238 here, okay, uranium-238 here, and then it goes to the excited state and it becomes uranium-239, okay, there has to be some energy that it should absorb, okay. So there has to be some energy that it absorbs. So it is not about electromagnetic radiations right now. We have got a neutron, and the neutron will give it almost a similar energy, because of which this uranium at this particular energy level will jump to the excited state. But then there is a problem here, that it's not mandatory that a similar energy level will exist. Okay, so if it does not exist, then what happens? If it exists, that's resonance. Okay, if it does not exist, resonance might not happen. So let's just have a look here. Okay, so just read these sentences. This is actually very important. Whatever I said is going to be explained here. So let's say I have got the energy. Yeah, anyone has a question? I think someone's mic is unmuted. Noincha, you have a question?
No, sir.
Okay, no problem. Yeah. Okay. So as I was saying that we do have this energy now. So let's consider that the energy is not less than the energy that we are talking about here for exciting a neutron. Understand this. For exciting uranium-238 from this energy level to this energy level will be given by Q plus K 1 minus Mn divided by M239U. So mass of this and mass of this is fixed. This is not something which I can play around with, but I can adjust the kinetic energy of the incoming neutron. Okay. So now this is simple. Now imagine you have a energy level which is, let's say, greater than 4.86. Let's say it's here, and it is not 4.86. Now if this energy is very less, then this part will be considered as zero. Understand this, okay? This part will be considered as zero. So that means if the energy gap is 4.86 MeV, then we can say that the new uranium-238 will become uranium-239, okay, in the excited state. But then if this energy gap is larger, how do I carry out a reaction so that uranium-238 becomes uranium-239 after neutron is incident? How do I do it? I simply increase the kinetic energy of the incoming neutron. If I increase the kinetic energy of the incoming neutron, this energy will increase. And I can adjust it in such a way so that it is exactly equal to the energy gap between these two. Okay. So now the question is, can this value be less? Okay, it's higher, fine. Can it be less? The answer is no, because we are calculating it from the Q value. So if there is a reaction where a neutron is bombarded uranium-238 is bombarded by neutron and we get uranium-239. This is the minimum energy that we actually have. Okay, so even if there is a lower energy existing, okay, yeah.
Sir.
Hmm?
Sir, please scroll down your paper page slide one. Scroll down, please, sir.
कौन सा वाला? ये part? This
सर
part?
थोड़ा नीचे कीजिए स्लाइड को, वो जो ऊपर का दिखा रहे हैं ना
हाँ हाँ,
अभी
अच्छा यहाँ पे
एडिट करके
अभी
वो थोड़ा नीचे को
अभी is it visible now?
डाउनवर्ड, हाँ हाँ लग रहा है
अभी दिख रहा
ऊपर
है?
कुछ छूट गए थे इसलिए थोड़ा, हाँ हाँ सर.
अच्छा अभी clear है ना? Okay. So this is your energy level of 4.86 MeV. Okay, and then if you consider the Q value of this particular reaction, that means uranium, if there is an energy level at 4.86 MeV, okay, understand this, very important. Then even if you consider a very low energy neutron where kinetic energy is almost equal to zero, not exactly zero, almost equal to zero, so you can ignore this part, okay, then we can say that the neutron can go and the uranium can absorb the neutron and become uranium-239. But then if I want to excite this uranium-238 to become uranium-239 and want to carry it to a higher energy level, what do I do? As per this reaction, if I increase the kinetic energy of the incoming neutron, this energy will increase. So the energy available for uranium-238 to absorb, okay, and get excited and become uranium-239 will be more. So I can adjust it accordingly and allow the jumping of uranium-238 to uranium-239. And that is called nuclear resonance. So this is one of the best example to understand nuclear resonance, okay, instead of just writing down equations, okay. So let me just read through what exactly you might write in your exam, okay. But then if you understand it, you can always write it in your own sentence. So depending on what type of neutron we are applying in terms of kinetic energy. So whenever there is a nuclear reaction, you might have a highly energetic neutron, you might have a very low energy neutron, or you might have a medium range energy, okay? So depending on what kind of neutron, the type of a neutron means what is the energy that it carries, okay? The energy level higher is populated. So now you understand this, okay? It's populated. Now imagine if there is no such energy level. So for example, if I say that there is no energy level which exists where the energy gap is 4.86 MeV. So there will be no such energy level present, okay? Then what happens that the neutron has the probability of that reaction is less. So that means what happens is that if I'm using that particular neutron, okay, which is low energy, because of which you are having the Q value as just 4.86 MeV or delta E value as 4.86 MeV, and there is no resonance, that means there is no energy level which exists at 4.86 MeV, that means the probability of that nuclear reaction happening is less. Okay, so this is important. This is this. Now I want that there should be a nuclear reaction because I'm interested in making uranium-238 to uranium-239. What should I do? I should play around with the kinetic energy. Okay, so this is what is the next sentence. So the probability will be high for those reactions where the neutron gets absorbed, okay, and hence there exists a corresponding energy level. So there will be a corresponding energy level, okay. So this is actually called the resonance, okay, nuclear resonance, okay, and this is important. And if you actually plot a graph between the kinetic energy, okay, this is a very simple idea, okay, the kinetic energy and the nuclear cross section. So you understand what is nuclear cross. I forget this part now. This has been omitted. This is just some words. So if you are actually plotting a graph between the nuclear cross section and the kinetic energy, you understand that the cross section will actually give me an idea of what is the probability of absorbance of that particular neutron, right? So if there is a graph plotted between the nuclear cross section and resonance, and the kinetic energy, it can be observed that at certain point there is a peak. So let's say at this particular kinetic energy, the probability of absorbance is more. Absorbance is more. That means the resonance is happening there. So what does these points represent? These points might represent the level at which the energy exists, okay, or the energy levels in general. Let's say, for example, if this is 4.86, see, 4.86 is something which is there because of the Q value, and if these values are beyond 4.86, let's say I have an energy level at 2 which exists, so I will adjust this value of kinetic energy so that I am able to allow that neutron to be absorbed by uranium-238 to become uranium-239. Okay, and in terms of the quantum mechanical expression that we have, that will actually be given by the cross section. So this will actually give me the probability of the capture will be high, and that's why we get a peak. So we have got 1 peak, 2 peak, and it might be more and less. Okay, so this cross section will always represent probability. So we have got a very high peak, that means at that particular point the probability is high, at this particular point the probability is a bit low, and so on. Okay, so this is actually called nuclear resonance. So what does these peaks correspond to? These peaks corresponds to energy level of uranium-239 beyond 4.86 MeV, and they are discrete. You cannot really predict at what energy level they will exist, because you see, for normal examples, if you consider the energy levels of an atom, or if we consider the energy level of let's say the neutron or the proton, whatever we have studied from the shell model, or even the splitting cases that we have seen, we do understand that these energy levels are not equally distributed. So if they are not equally distributed, the energy needed for jumping from energy level 1 to 2 and let's say from 1 to 3 will be different, right? Because both of them are having different gaps altogether. Okay, 1 to 2 will be different, 2 to 3 would be different, it won't be the same. So that's why they are discrete in nature, and that's actually the property of quantum mechanics. That is how energy levels are divided, and that we know. Okay, so this is what is nuclear resonance is all about. Okay, so this is what happens, and this is what we call as nuclear resonance. So this phenomenon, okay, is known as the resonance, where the cross section suddenly shows peak for certain kinetic energy of neutron. So let me tell you, I have checked some books. They do explain a lot. Okay, in some books they are doing it very short. Okay, very short. But then I think this is where I have striked a resonance here. Okay, so that I am able to not explain too much, but then we are able to cover what is exactly meant by nuclear resonance. Okay, so this is actually important in fission reactor. Why? Because you understand this, right? You have a neutron. Nuclear reactor is also a part, but I think nuclear reactor all of us have studied before. We have a neutron, it's hitting a uranium, and then it is getting parted into 3 neutrons, and then it gives out some other atoms, right? But then these neutron needs to be controlled, and then we use those cadmium rods. Okay, then also why we down neutron of reaction happening, maximum probability of uranium-235 converting to uranium-236. Okay, so that is what is the idea of fission reactor is all about. So if we slow down the neutron, that's we are playing around with the kinetic energy of the neutron. If you are playing around with the kinetic energy of neutron, the probability of a nuclear reaction happening is more. Okay, so this is the twist that you have basically when you study your MSc syllabus. In BSc syllabus, हाँ neutron है, reaction hona hai, we slow it down and we allow it to hit uranium-235, it becomes uranium-236, unstable, breaks up into 2, gives out energy, right? So that is what we understand. But then if we go deep into it at this particular level, we have to understand that this will only happen if there is something which we call as the resonance phenomena that is happening. So that is important. Okay, so these shapes that has been worked out here, okay, can be actually worked out theoretically, okay, with the help of these tools and all. And this shape is basically called the Brigner-Witt formula. So it is worked out theoretically called the Bright-Wigner formula, not Brigner. Bright-Wigner formula. Okay, so this is actually a part of your syllabus, and then this is partly qualitative, partly quantitative. So you have to remember this reaction and implement that reaction to understand what is. Okay. So the idea is simple. I hope I have explained it clearly, but even if you don't understand it, okay, I will definitely put the recording for you all to check. Okay, that's important. Okay, so let's just do a bit more. Okay, we are going to talk about fission reaction in the next class, but then before we go into this, I think this idea is already clear to us, so let me just explain it once. Okay, so this is actually nuclear fission reaction. So when we talk about a fission reaction, so now we know what is resonance. has happened, and then we are expecting that there is a heavy nuclei, let's say for example uranium, okay, which breaks up into two light nuclei, let's say barium and krypton. Okay, so this is what we are going to study now. So we're going in a sequence so that we understand each of them step by step. So we do have a heavy nuclei, okay, and this heavy nuclei is, let's say, X, which is uranium-235, and it breaks down into two light nuclei, which is, let's say, Y plus Z. So this is just an example, okay. Let's take X is Y plus Z, okay. So if we know the reaction scheme for nuclear fission, okay, we know that neutron will actually hit uranium, okay, and then it will give out your barium and of course krypton, okay. But you know, there is an interesting story behind this, that barium was originally not there when nuclear reaction happened, and actually barium was the element that was created. There was no existence of barium in the periodic table. So since it showed behavior which was similar to uranium, okay, it did have some radiation possible and so on. These kind of elements are called transuranic.